Hello, everyone. Sort of the last everything week in 6004, and everything week wouldn't have everything in it if it didn't have a quiz, so we have one on Friday. There's lots of information about what it covers and things like that on the announcements page, so look there. There's some review videos you might look at if you'd like. Do some problems from previous years. There's been a lot of conversation in Piazza about when things are due. Basically, you need to get all your checkoffs done by the last day of classes. So 5 p.m. a week from Thursday is the deadline. I have to say, in the legal fine print, that a lot of that represents an optional extension that you can have because we're actually not allowed to have a lot due the last week. So it's all due this week, but you can take till next week to turn it in. So you're welcome. I hope everybody noticed, by the way, that he actually has a little pipeline diagram stuffed up under the brim of his hat. So, you know, thank goodness the semester is coming to a close. 6004 jokes are getting slightly desperate. So, okay. So when we left our hero last time, we were struggling with this, you know, we're sort of halfway through our journey of saying, okay, we've pipelined the processor. Remember, we drew stripes across the fish, and now we're sort of trying to make sure it's still a fish. In our case, we're trying to make sure we can still execute programs correctly. And we talked about the problem of making the branch decision in the RF stage meant that the instruction that was already noodling its way through the stage before, the instruction fetch stage, the IF stage, was already in the pipeline, and so we had to sort of annul it. We chose to, by default, annul an instruction when the branch was taken because we didn't want to execute the instruction. That was the instruction following the branch, which only happens when we don't take the branch. And then we moved on. We're currently looking at a 4-stage pipeline, although quickly today it will become a 5-stage pipeline. But we have a 4-stage pipeline, and we're noticing that this set of instructions here, where we are producing a result in one instruction, in this case the add is producing its result in R3, is being used as one of the operands in the subsequent instruction. And so if we think about this a little bit, because of the way the pipeline works, the add actually writes its answer into the register file at the end of cycle I+3. And that means that starting in cycle I+4 and beyond is when the updated contents of R3, the new contents that were updated by the result of the execution of the add instruction, okay, are available in I+4 and after that, and subsequent cycles. And so that was fine, except that we have this poor compare in cycle I+2 in the register file stage. And the job of the register file stage is to go fetch the operands that the compare requires, in this case the contents of R3 and the constant 100. And if we can't look on the register file because it's not going to be there, in fact it's not there in cycle I+2, and in fact it's not even there for all of cycle I+3, it's only at the boundary, the clock edge separating I+3 plus I+4, where the content finally gets written. Okay, so we're sort of going, oh, well, we need to fix that problem. And so the way we chose to fix it was to go off and resolve the problem by noticing that the information that we wanted was actually coming out of the ALU. That add instruction was, when the add instruction is in the ALU stage, the output of the ALU towards the end of that cycle is, in fact, has the actual binary bits. Well, you know, it has the number, the integer that will be written into the R3 register at the end of the next cycle. So we actually have the number we need, it's just not in the register file. And noticing that we actually have the number we need suggested to us that we could modify our data path, that when you wanted to get the contents of a register that was a destination register of an instruction that was ahead of you in the pipeline. In other words, an instruction that came before you in the program, so it's ahead of you in the pipeline. We actually, in this particular case, already will have the information that we need. And in fact, if we could somehow get it from the coming out of the ALU and back into the RF stage towards the end of cycle I+2, we'd be sitting pretty. We'd have what we wanted. And so, in fact, we've introduced this notion of bypassing. The notion we've added an ability for the RF stage to notice when instructions that are ahead of us in the pipeline are producing the result we want. We can actually forward it from those pipe stages that are ahead of us. So from the RF stage point of view, currently the stages that are ahead of us are the ALU stage and the write-back stage. And so we can sort of reach up and say, I'm going to borrow that number. I know it's going to be in R3. I'm going to look. I want the contents of R3 as a result of executing the instructions ahead of me. And you know, that number is there. So we'll simply put some extra multiplexers in our data path to allow us to select that as one of the sources for the contents of a register. So not only can I get the register from the register file, the contents of a register from a register file, I can get it from the output of the ALU, or I can get it in the write-back stage. And after that, of course, it would be in the register file, and I don't need to get it from any other places. Okay, so we could deal all this in software, but we've chosen to go ahead and add that special hardware and do the forwarding. And in fact, if we go off and analyze what's happening here in the diagram, we can see the multiply, which also wants R3, can also get it from the write-back stage. Notice it's not quite in the register file yet. It only gets in the register file I+4. So the multiply is getting the information it needs from an instruction that has proceeded it down the pipeline. The compare instruction is actually getting both of its operands from different pipeline stages. And so we have to make sure, of course, that we can bypass for both the contents of the RA register and the contents of either the RB or RC registers, depending on what the value of the RA2 cell mux is. Okay. And, you know, here's a sort of a quick and dirty sketch of how we need to modify the actual data path. And what we've done is to put some multiplexers in that allow us to go ahead and instead of taking the output of the register file, to instead also fetch the number we're looking for from either the output of the ALU or perhaps the output of the WD cell mux. So any questions about that? It's just really a way of getting the number we want that we know will be written into the register file. It just hasn't arrived there yet. So it seems like a lot of extra hardware, but the advantage we're getting of that is that perhaps our processor is running 3 or 4 times faster than it had before. So we're trading some extra transistors for hopefully a much speedier execution. Okay, and we're saying, oh, this is great, good. So we're done pretty much, I guess, with bypassing. And so in fact, if we look at this little picture, we'll see that there's one little fly in the ointment. And it's a fly in the ointment that will cause us to have to add some more mechanism. So in fact, if we think about what's happening here, that add instruction actually needs to be able to read the contents of the memory location whose address is R1 plus 0. In other words, this load instruction is going to compute the address and then go off to memory to fetch the information and stick the contents of that addressed memory location into R4. Add wants that, and you can say, well, okay, it turns out if I think about the XOR instruction, so the load is down here in the write-back state. I haven't solved the problem with add yet. That's the fly in the ointment. But the XOR instruction is okay because the load is down here, and in fact, this is the cycle down here in the write-back stage that the data memory is actually coughing up the value we want. In fact, the value we want will be coming out of the WD cell mux, which means that, at least in the case of XOR, I can go ahead and bypass it back. And for some reason, I carefully bypassed it back into the A operand, even though it seems to be the B operand. So that arrow should probably be going over here somewhere. Okay. Everybody happy with that? So the XOR instruction is no problem. Our bypass pass take care of it. The trouble is that the add instruction doesn't work. And why not? Why is it? What's going wrong? Why isn't the information we have? When the load is in the ALU stage, what is actually coming out of the ALU? What do we use the ALU for when we're executing the load instruction? Yes? we're actually computing the address. So what's coming out of the ALU is not the information we want, it's the address of the information that we want. So the ALU is performing this addition, in this case of R1 plus the constant 0, and that's what's available coming out of the ALU. That is not helpful to bypass it from there. And in fact, nowhere in the machine is the information we want on some wire that we can bypass. It's still in the memory. We haven't even started the memory fetch yet. Right? We've just computed the address, and we're about to start the fetch into memory. But we haven't done it yet. So in fact, there's really no way in which the add instruction can complete its operation in the RF stage, because it simply can't put its hands on the contents of R4. It's the result of the execution of the load instruction, and the load instruction simply hasn't gotten far enough along for what we want to be available to us. Does everybody understand the struggle here, right? We're looking for a value, and when we wanted the output of the ALU, that was okay, but we don't want the output of the ALU. No place to bypass it from. Okay, so here's sort of a graphic representation. What's coming out here now is the address of the memory location. You can see it's not in this 4-stage pipeline, not until the write-back stage that we actually go do that fetch. So the add instruction simply can't go anywhere. It has to stay in the RF stage until the load instruction moves forward one more stage in the pipeline. Okay, so we're going to have to introduce some notion of stalling. So if you look carefully here, you'll see that as I go from cycle I+2 to cycle I+3, the RF and IF stages are stuck. They've been stalled. We're not actually, whatever instructions were in those two, well, in this case, the add and the XOR, are sort of stuck there, and they're going to come back for a repeat appearance in cycle I+3. Because the add instruction, we can't get the operands yet. We have to wait until the load instruction is down here. Once we can, then we can do the bypassing, and away we go. And because the add instruction is stuck in the RF stage, the other instructions that come later in the program, okay, or earlier in the pipeline, okay, they come at earlier stages of the pipeline because they're later in the program. They just have to wait in line. They can't move forward either. They're behind us. They have to wait for their turn in the RF stage. I'm sorry, occupado, right? I mean, this stage is occupied. So the add instruction, because it's stuck, means that the RF stage is stuck at the same time. So we're going to freeze the top part of the pipeline so the instructions simply don't progress down the pipeline. And that fixes our problem. The ability to freeze the pipeline fixes the problem and allows us now in cycle I+3, now the data we want is coming back from memory towards the end of the cycle, and it can be bypassed, and we can get that R4 operand. There's one other small detail, which is that's fine. The add instruction has to stay here, but since the add instruction didn't move down the pipeline, but the load instruction did, in fact, we wanted the load instruction to move down the pipeline, what should we make the ALU do? Right? I mean, it's going to be sitting around saying, look, I didn't get a new customer. I didn't, the RF stage didn't send me anything. I don't really have anything to do, And so the answer is it's going to be a slacker, right? I'm going to do a no-op. So what I'm doing is when I freeze the pipeline, I start putting no-ops in for the down stages, saying, I don't have anything for you yet. Here, do nothing. So, okay, so what do we need to do? We need to go off and add some load enables to the registers here in the IF and RF stages so that, in fact, we can choose not to load them. So we have a stall signal, and in fact, when we take the inverse of the stall, so when stall is asserted or 1, not stall is 0, which means these registers, the load enables of these registers are 0, meaning they don't load. So those registers won't change their value at the end of the cycle. We also need to insert a mux here, which allows us to replace the add instruction, which is stuck here. So at the end of the cycle, we're actually going to load in a no-op. So we're going to allow ourselves to multiplex in a no-op here for subsequent stages. We have to tell the subsequent stages to do nothing. Suppose we didn't care and just let anything we want happen. Would that be okay? I mean, why are we so anal about saying, no, I have to give you a particular instruction that does nothing? Why don't we say, oh, we'll just make the signal lines be random? What would be bad about that? Yes?
You're busy fetching a specific address, so if you had to do something, you would change that?
Right, you have to be a little careful about what these guys are doing unsupervised. If you let them unsupervised, they might say, oh, I can do anything I want. How about a store into some random memory location, right? So, the answer is that would be a bad idea. Don't leave your teenagers home at night unattended. Well, don't leave your pipeline doing anything it pleases. Really, Mom? Anything I want to do? The answer is no, no, dear. You can't write into main memory. Okay, so my household is strange, as you can imagine. So what we have here is a situation where we actually have to tell all the, be very explicit. And so we put in this no-op just to make sure it's not inventing something, not good to do. In this case, affecting the contents of main memory, or perhaps writing a random value into a random register. Those are all bad ideas. So we put in a no-op that makes sure that no state will be changed as a result of saying, do anything you want. Okay, so then as things move forward, we put a no-op into the ALU stage, and the load proceeds, and we're all set. Okay. So we have this notion of, well, okay, this is great. Now, let's talk a little bit about the memories. I've always complained about the memories being slower. So there's really, you're going to say, well, pipeline stages, that's neat. Suppose I have a memory that takes 10 cycles to actually, between when I give it the address and when I get back the data. And that's sort of the situation you're in now. Your memories are very slow compared to the, the nanosecond or half a nanosecond it takes to execute an instruction on your processor. And so the memories, will take 30 or 40 cycles to get back a value. And so you can say, well, I'll just add 30 or 40 pipeline stages. So we'll make the memory this giant pipeline system. And you can say, okay, but that means we'll spend all of our time stalling. This poor guy is stuck in the RF stage while we're waiting for the 40-stage memory to finally produce an answer in the write-back stage. And so we can bypass it. And you're sort of going, wow, bypassing really helped us there, didn't it? It was 40 cycles instead of 41 cycles. So, and so the idea here is that the long memory times are creating a bit of an issue. Well, we can start down the path of, for instance, adding a 5th pipeline stage here, like so. Usually what really happens is that in the so-called memory stage here, the extra pipeline stage here, we're checking the caches. And then if the caches have a value for us, we write it back in the write-back stage. So I think of this memory system as being both caches and main memory. And in the case when we don't have the information we want in the cache, we're sort of stuck, and everybody has to sort of freeze until we can't go any further until the memory system completes. But if we have it in the cache, if we can check the cache, say, in this cycle, then in fact, we can bypass it from the write-back stage, and away we go. So this extra pipeline stage is really an accommodation for the cache, and we've just shown the memory system is a combination of cache and then something that takes almost forever. But that doesn't solve our problem in the case. So this 5-stage pipeline helps us a little bit, particularly if we have caches in our system. It doesn't solve our problem in the case of really slow memories. So what's the modern solution to this? The answer is you have to get the information from memory. Memory is going to take a long time to get back to you. Okay, what should you do? So is your processor spending all the time stalling when it's reading and writing memory? The answer is no. Intel has thoughtfully invented hyperthreading. So what is hyperthreading? You all carefully paid the money to buy hyperthreading. Yes?
It's like basically they switch to like another process while it's waiting for memory.
Right. So the idea is if I had something else I could do, and the something else might be another program. Suppose I had just another whole copy of the register file. I could spend transistors to sort of give myself an opportunity to quickly in one cycle switch to another whole program in the hopes that maybe that program would have an instruction that I can have start wandering through the pipeline. Okay, while waiting for the memory system to get back to me for program A, I might be able to do an add for program B, or typically the threads. You don't change the context, you only change sort of the active running, the active register contents. Okay, so the idea in general in modern high-performance systems is to say, I don't have only one thing to do, which means if I'm stymied doing that one thing, I have to sit around and do nothing. In modern systems, the idea is to have a whole collection of things to do. And when you're stymied on one thing, you go off and work on something else. Now, of course, this is a strategy you're familiar with. I can't get problem 4 on the 6006 problem set. Do I wait all week until I get the answer? Or do I say, well, maybe I'll go do the 6004 lab or read my HASS assignment instead? And so you guys are naturally hyper-threading sort of people, right? And processors have saw how well you guys worked and are following suit. Yes, sir? So this diagram doesn't have the annulments. Well, I'll start putting them in again.
Why don't we do annulments instead of stalls?
So there's a difference between annulments and stalls, right? An annulment means is when we actually throw away an instruction. We replace an instruction that would have been executed with a no-op. So that's what happens when we take a branch. We actually throw away the instruction following the branch. A stall, we actually will execute the instruction at some point. We just can't finish executing it now. So they're really different. And so there's two ways no-ops get into the pipeline. One is when I'm replacing an instruction. One is when I'm filling in an empty spot in the pipeline, but I'm actually not replacing any instructions in the program. So no-op is not a sign of annulment everywhere. Sometimes it's a sign of I got to tell you to do something while we're waiting for the right thing to happen. Okay, so we wanted a clean, simple pipeline, so we had the ability to do a no-op here. And remember, the no-op in this stage was actually an annulment no-op, the replacing of an instruction we did not want to execute. We inserted a whole bunch of bypass paths. I love this sort of heart shape. So think heart when you think bypass. And you can see that what we're doing is taking the values from downstream pipeline stages, instructions that came ahead of us in the program and are ahead of us in the pipeline, and grabbing their values before they actually get written into the register file. Okay, and then we had to add the ability to freeze the top half and insert no-ops while an instruction was stuck in the RS stage while the load made its way all the way down to the write back stage so we could grab its values. So this particular no-op, at least at this stage in the lecture, is really there so that I can wait for loads to, for the memories to complete and for me to actually have the value that I need to get for any instruction that uses the result of the load. Just to make really crystal clear the picture of where the bypasses go and everything else, the bypasses actually go sort of right next to the register file. All of our logic that operates on the contents of a register, where we, taking the jump address or testing to see if a register is 0, or feeding the value into the A cell mux or the B cell mux to select between, a different number in the register contents. All of these things operate on, quote, the value of the register. This mux is selecting the correct register value, either from the register file or from downstream pipeline stages. And so this wire coming out of the bypass mux is, quote, the correct register contents. Everybody got me on that? So we've just sort of randomly been drawing, multiplexers in the RF stage, and now on this slide I finally am very careful about showing you exactly where that goes. Okay, so we've been a little sloppy about that, and we've cleaned that up. You might say, oh my God, this is a 17 input, 32-bit mux, isn't that sort of big? Well, if this was a VLSI class, I could show you some pictures showing you how to implement that very, very compactly. And in fact, you could do some neat tricks with tri-state drivers to build a mux, and you can do the layout of your system in such a way that it turns out this is not a very expensive thing to do, even though it looks horribly expensive the way we've been drawing it. 32-bit buses going everywhere. It's not as bad as it seems. So, take 374 or 823 or something like that. You'll see some pictures that might convince you that this bypassing thing isn't quite as brain dead from an implementation point of view as it appears. Okay, a couple other things to think about. This very strange program, which I don't recommend for anything in particular, except to sort of show you that, in fact, we have this situation that, that we need to figure out. Here's the branch register writing something in the LP register, and I'm branching to a location that's going to use the LP register. And what we're pointing out is that not all of the information that we want is in that middle vertical column of our processor diagram. By the way, if you look on the last page of your handout, you'll actually see your 5-stage pipeline in all of its glory, not in microprint, so it's a little easier to follow. And so the middle stage I'm talking about is basically register file to ALU, down to the WD cell mux. So far we've been doing all of our bypassing from there. The point of this particular strange program is to sort of observe that occasionally the contents of the register don't come from the ALU or from the memory. Where else can the register contents come from? There's one other input to the WD cell mux. So look at the very bottom, and you can see, look, things that can go into the register file are basically the output of the ALU or the output of the memory or PC plus 4, right? And when do we write PC plus 4 into the register file? For instance, when we do a branch, a taken branch. Okay, so when that happens, what we need to do is sort of observe that we need to not only bypass from all of this stuff over here, we need to also include bypasses from the other things that can go in the register file, in this case the PC plus 4 value, which is dutifully also flowing down the pipeline. So it turns out that our bypass muxes are even piggier than you thought. Not only are they bypassing 32-bit values from this wire or down here, but we also occasionally have to be able to bypass them from the PC plus 4 values in the ALU or MEM stages. Okay, how do ILOPS work? Well, we've already talked about how to do that in a single processor, right? We detect an illegal operating system, and we're going to force a procedure call. They're discovered in the RF stage, right? That's when we actually, for the first time, have the instruction and are busy decoding it. So it's in the RF stage that we're going to detect that we actually have an illegal instruction. And now the question is, what should we do about it? Okay, we have an instruction in one of the pipeline stages that seems to be, we can't execute it. So what's our strategy for dealing with instructions we can't execute in the pipeline stage? Well, if we can't execute them because we just have to wait for a while, we employ a stall strategy. But if we can't, we'll never be able to execute this illegal operation. In fact, we need to do something else entirely. What should we do? And the answer is, we're going to, oops, I skipped past the magic answer. The answer is we're going to synthesize an instruction to replace it. And the goal of this new instruction should be, its only purpose in life is to capture the PC plus 4 value. Right? So we're going to take the illegal operation, which is now in the RF stage, and replace it with this instruction here, which you can see it doesn't branch. R31 is never not equal to 0. And so we're not going anywhere. This branch is really but the other side effect of the branch, besides changing the PC value, is to write PC plus 4 into a register. So we synthesize this instruction, and the rest of the pipeline stage will go, oh, for me, what this means is to capture the PC plus 4 value in the XP register. So that's the purpose of this rewrite. So in fact, the multiplexer here that's busy rewriting the instruction in the register file stage. So we had one input here that rewrote it as an OOP. We also have a way of rewriting it as as this magic B&E with the destination register of the XP. That's what this here is. And then when that makes its way down the pipeline, that'll capture the PC plus 4 value, which is exactly in the XP register, which is exactly what we did in our standard implementation, right? We just have to sort of shuffle our feet a little differently here because we have to let that happen not in this stage when we discovered the error, but we have to send a message way down here to make sure the WD cell mux is set correctly and the register file writes the XP register. And the way we sent that message down 2 pipeline stages was simply to synthesize an instruction that says, when you get this, do this and you'll do what I want. Does everybody sort of get that idea? The whole goal here is to send a message a couple pipeline stages down, and the way we're doing it is rewriting the instructions so the pipeline stages will do what we had in mind as the result of the illegal operation. Okay, well, it turns out that ILOPS aren't the only reason you might not be able to complete the execution of an instruction. In the ALU stage, what might happen? You might divide by 0. You might have some sort of error. that says, look, I don't have any good number to write into the destination. I want to stop execution of the program at this point and instead go off to some sort of kernel trap handler that can print you a backtrace or make Python print a backtrace or something that noticed that instead of failing silently and writing garbage, the arithmetic unit may say, this is not legal. I'm going to stop your program execution so you can go figure out what's wrong. What sort of operation might go wrong in the memory stage? We can think of two. One is you might access an illegal memory address. The bottom 2 bits aren't 0 of your address, or you're accessing a region of memory that's not there. Or, it might not, you have a memory management, you might have to be taking a page fault. So once we have the address, we go check the page map. It's not resident, so we want to take a page fault. So we really can't execute this instruction here, whatever it was, the load or the store. So in fact, what we need to do is to stop execution. We need to rewrite the instruction where the fault was discovered into one of these magic B&Es, please capture PC plus 4 for me, into the XP register. And what do we do with all the instructions that are behind us in the pipeline, that became after us in the program? What should we do with them? So we're down here, we're saying, oh gosh, this load, we can't finish that, we have to take a page fault. What should we do with the instructions that follow the load? They're in the pipeline. Well, should we execute them? How many people think executing is a good plan? That sounds like a very, medieval sort of statement. Kill them all! That's not what I meant by executing. Should we actually do the instructions? No. So the thing is that we're stopping the program execution at this load instruction. All of these instructions that follow the load are like they shouldn't be executed. So we mean execution in the other sense, right? We need execution we need to stop executing the instruction. We don't want to execute any of those instructions. How do we arrange for an instruction to go away in the pipeline? Replace it with a no-op. Okay, so, you wander around and everybody's sort of saying, oh gosh, that's a bad idea. You can say, replace it with a no-op. And everybody will go, whoa, boy, of course 6 people are strange. Okay, but now you have a new term. I'm going to no-op an instruction, which basically means I'm going to take it out of the pipeline and replace it with a harmless thing to do instead. So this operation of when you detect a fault, rewriting that to capture PC plus 4, so that means execution is now halted here, and flushing the pipeline. So we're going to take all the other instructions that come earlier in the pipeline. Okay, that means they come after the faulting instruction in the program. They're earlier in the pipeline. With all of those instructions going. What about the instruction down here in the write back stage? That's okay, it can finish. It was okay instruction, it's just finishing up. So whenever the fault happened, we rewrite it with a B&E, destination register of XP, and we throw away everything else. We flush the pipeline. So these sorts of traps are expensive. We're throwing away lots and lots of execution. Typically, they represent an error condition or a condition that will take hundreds of instructions to fix, like a page fault. So throwing away 3 and 4 instructions is not a big deal in the scheme of things. Yes, ma'am?
When you come back, will you then have to skip backwards because...
Right, so the PC plus 4 is actually pointing to the instruction after the one that stopped. So in these particular faults, we have to basically say, ooh, guess what? We actually have to back up the XP and to see where the actual faulting instruction was. Okay, what about interrupts? That's the final, thing that we want to deal with here. So the interrupts, well, actually, this seems like it might work pretty well. Suppose we want to have an interrupt happen between the add and the sub instruction. We want to say, okay, we want to do the add, but we want to start executing someplace down here in the interrupt handler. So after the add, we want the next instruction to be executed to be the first instruction of the interrupt handler, which is the OR instruction. We don't want to do the sub. Okay, well, it seems like maybe we could just use our rewriting mechanism perhaps to do something interesting. Suppose we decide that we can figure out in the IF stage that we want to take an interrupt, right? And so what we do is instead of fetching the sub instruction, when the so-called interrupt, we recognize the interrupt in the IF stage, we could then, as the add now goes through the pipeline, we at this cycle say, psst, IF stage. Instead of fetching sub, go off and fetch, the first, this magic from whatever the magic low core, 8004, 8008, whatever the magic, places are, the interrupt handlers live, go fetch the instructions there. So it seems like this is a good plan. We have a way of, without wasting any cycles, no instructions to throw away. If we make our decision in the IF stage, then there's no unfortunate instruction that got fetched into the pipeline that we don't want to execute. Right, so this seems like a good plan. It has, unfortunately, more flies in the ointment. Someday someone's going to come up with this big jar of goopy stuff with flies in it and say, here you go, Chris. 004 in a nutshell. Flies in the ointment. Okay. Okay, so the problem is that in addition to switching the instruction stream from the add down here to the interrupt handler, we have one more mission, which is we have to remember where to resume execution of the program we interrupted. And the way we remember that is we need to basically write the PC+4 value, in other words, in this case, the address of the sub instruction, into the XP register. If we look down here in the write back stage, you can sort of see that our dance card is full. There's really no cycle in which we can say, okay, by the way, register file, could you please write this magic PC+4 into the register file? We were very clever here at sort of keeping things going, executing only the instructions we want, but we were too clever and we didn't leave ourselves time to write the PC+4 value. So instead, we're going to take the instruction we want to interrupt, and instead of executing it, we're going to rewrite it as one of those magic B&E, please capture PC+4 into the XP register instructions. So that means that we actually, the value that we're saving in the PC+4 thing represents, we haven't executed the instruction before where that XP register is pointing. So we have to be a little bit more clever. Okay, but do you see sort of how so what is it we're doing with instructions? Occasionally we rewrite them with no ops when we don't want to execute them. Okay, when we're throwing them away, we're annulling them. Right? And when do we see ourselves rewriting things with no ops? In the case of branch delay slot instructions, when we took the branch, we don't want to execute the instruction that was in the IF stage. And also when we're flushing the pipeline, we detect some fault in some pipeline stage, and all the earlier stages, all the instructions in the earlier stages, which come after the faulting instruction, actually have to be rewritten as no ops so they don't actually get executed. Okay, the other thing that we rewrite is this magic B&E, please store PC+4 into the XP register instruction. And we use that whenever we're going to stop execution. So in this case, we did that when we detected instructions we couldn't execute. ILOPS in the RF stage, arithmetic faults in the ALU stage, memory faults in the memory stage, so forth and so on. Okay, so we have this rewrite, and that gets the job done. Okay, so all that's good. We have a way of basically rewriting this add as a B&E, which means the add wasn't executed. So at the end of the interrupt handler, we have to remember the XP register is now pointing to the instruction after the add. We have to back it up, so we're now, the XP register is pointing at the add instruction, and then we do this jump. So we're making a small correction. We know what the hardware has done. And so we're making a small correction to the XP register before we use it as the place to resume execution of the user program. And all that's taking into account which things which instructions we have executed and which we haven't. So all these little details, right? Jiggle here, oh God, another mess to fix up. So we've been following the dog around the apartment for 2 lectures now, cleaning up after it. Okay, let's see sort of where we got to. So here's our final version, right? And what have we done? We certainly added the pipeline registers. We've added lots of ways to rewrite instructions, right? And the way we've added to rewrite instructions is we can take an instruction, you can either replace it with a no-op or with a B&E. And there's very specific situations, okay, at each stage as to why we might choose a no-op and why we might choose one of these B&Es. And you should understand, why would I be putting a B&E in this stage? When would that happen? So you should say to yourself, okay, notice the control signals here, these annul control signals, right? So these annul control signals are basically selecting, they're the rewrite control signals, and we can either execute the instruction, rewrite it as a no-op, or rewrite it as a B&E, capture PC plus 4 and XP. And there's very specific situations in which we do all of those. And in fact, if we do something in one stage, usually the earlier stages are busily putting in no-ops to get rid of the instructions that will no longer be executed. Whew. Okay, so all of this, so the bypass muxes and then all of these rewrites, okay, in addition to the pipeline registers were added. What do we get for having added them? Let's loop back and try to remember why we put ourselves through this pain for close to 90 minutes now. I don't know, Chris. We needed lectures 22 and 23. You filled them with something. Should I think of it as a no-op? Were you filling our pipeline stages for us? What was the point of all this? Speed. Pipelining. The whole goal was to do the pipelining. And how do we get something to run faster? Because what we did is we take all the things that take time, we put them into separate pipeline stages so they can be happening in parallel. So if it took 100 nanoseconds to do all of this, our hope is that we've broken it into 5 20-nanosecond chunks. If we stand in the write-back stage, that would mean that once every 20 nanoseconds, we're writing a new answer into the register file, which means that we're effectively executing instructions 5 times faster than we were before. That's the whole goal of the pipelining. Sounds good. How many, is it likely we've achieved exactly a 5 times speed up? Lots of people going like this, which is a good thing to be doing. Where might we have gone wrong? Why wouldn't we get a 5 times speed up? I was selling you this used car just a minute ago, and it sounded good. Yes?
Some of the pipeline stages might take longer than others.
Right. So what happened was that we haven't exactly divided the delay up. Right, so we might get a factor of 3 out of this, maybe. I'm just guessing now, but it's not going to mean only if the gods were really with us would we actually get a factor of 5. Could we get a factor of greater than 5? No, 5 would be the best we could do. Okay, we're likely to get, and then you say, well, don't forget, Chris, you've been no-opping instructions right and left. Remember when we no-opt instructions? Because of branch delay slots, because of the structural data hazards caused by the load data hazard where we had to sort of stall the pipeline. And so we're, not only are we not getting a 5x speed up exactly, but we're introducing no-ops now and then as our, the final solution to deal with instructions that we can't really think of something else to do with. We can't correctly execute, so we replace them with no-ops. And so the extra no-ops and things like that also, effectively slow things down because they don't really count as executing the user program unless you guys write really dumb user programs. Yes, 700,000 no-ops. Okay. One last run. We started with a neat single, cycle execution beta. The diagram, to this day, I've given this lecture for decades, or the beta lectures for decades. I'm always amazed at how elegantly simple the beta, unpipelined beta diagram is. It's just got a couple blocks in it. If you went off and practiced, you could probably type a beta from scratch into JSIM in 15 minutes, right? A whole 32-bit RISC processor, right? So that's pretty neat. Okay. Then we started saying, well, let's make it faster. And the way we made it faster is we started pipelining it. So when we did a 2-stage pipeline, we get some increase in throughput, not 2x, but some increase in throughput, because now the time for the instruction fetch is being overlapped with the execution of the previous instruction, which is neat, or the execution of the current instruction is being overlapped with the fetch of the next instruction. Maybe that's a better way to say it. But we had to do some fixes because occasionally we ran across a situation, particularly after taking branches, that the instruction that was in the IF stage we didn't want to execute. Well, then we gilded the lily and went all the way to a 5-stage pipeline. And we had to add all these bypass paths because now the write back is happening to the register file cycles later, as the instruction actually has to progress all the way down to the last pipeline stage before the register file actually gets updated with the effect of executing that instruction. So that meant that earlier instructions that wanted that value had to get it from other places in the data path, which we could do almost everywhere, okay, except when we wanted memory data in the case of a load instruction. So now we had to start freezing the RF and IF stages and put bubbles in the pipeline, little no-op bubbles that trickle down through the ALU, mem, and write back stages. Okay, until the load gets to the write back stage, and now we can get the data we want. Okay, then we started looking into how to not only, so that was normal execution, and now occasionally we had to make sure that we could capture the PC+4 value, so we started figuring out how to do that. And in particular, if there's any sort of faults, we have to rewrite the offending instruction to capture PC+4, and then everything else earlier in the pipeline has to be flushed, meaning we have to actually rewrite them as no-ops. Interrupts, things were looking pretty until we remembered that we had to leave room for capturing PC+4, so a little fooling around with the XP register value got us that fix. All this extra hardware, overall, what do you think we've done to the size of a machine as it went from an unpipelined beta to a pipeline beta? Look at this diagram. You say, look at all the registers and multiplexers and extra data paths, and compare them in your mind to the sizes of these other things. Right. Of course, if the ALU has a multiplier, that's a pretty piggy piece of electronics. It's just a lot of gates. But without the multiplier, these things are probably comparable in size to the pipeline registers. I mean, to all the other pipelining hardware. So the pipelining hardware is a significant increase, maybe a doubling of the actual number of transistors you have to buy, leaving aside the multiplier costs. This is very rough sort of seat of my pants sort of guess. So pipelining was not inexpensive in terms of transistors, but we got maybe a factor of 3 or 4 in terms of execution speed, which in the modern era of Moore's law, with transistors becoming less and less expensive half as expensive every 18 months, we have lots of transistors to spend. So this was not a bad investment. Okay, I'm going to stop there. You'll have 3 minutes of your life you didn't know you were going to get, and we'll see you next Thursday. Last recitation is tomorrow. That's aside from, of course, quiz and section. So the last recitation, reviewing the pipelining stuff, is tomorrow. Lecture on Thursday, quiz on Friday, and then we'll see everybody working on their design project.